Hi guys, welcome back to 100 Days Machine Learning Crash Course. I hope you are doing well. Today we want to talk about some practical stuff and some practical issues in neural networks and in deep learning. So we want to talk about activation functions. We want to talk about data preprocessing, although we talked about data preprocessing in previous sessions, but we will talk about some advantages of data preprocessing and some commonly used things to preprocess the data. And we will talk about weight initialization, and we don't talk about checking gradients in here. I believe that it is not necessary to learn that now because we have a limited amount of time. Hopefully, maybe later we talk about checked gradients. Okay, let's move on. So we know that we have learned actually how a neuron works. So in a neural network, we call each of these nodes a neuron. So each neuron has some inputs from previous layer. So let's call it x1, x2, x3, and we have some weights in here, and so the input of a neuron is the sum of wixi plus the bias term, or if you include the bias as a 1 in here, you just need to have this term. And after that, this neuron applies a nonlinear function to this input, and we call it activation function. So we want to talk about how we should choose the activation function and compare each of them, and tell pros and cons of each. Okay, so in here we could see the list of most commonly used activation functions. We have sigmoid, we have tangent hyperbolic, we have Relu, Elu, Maxout, and Leaky Relu, which we will talk about each of them in next slides. Okay. The most common and the simplest activation function, which we learned about it already, is sigmoid. So sigmoid actually squashes numbers to range 0 and 1. In other words, for any number, for any real number, you could map this range to just 0 and 1, as you could see in here. Okay, so and the history of sigmoid activation function is that some neurons in the brain acts like sigmoids. So we saw that actually some neurons have a fire behavior function like this, and this sigmoid could be an approximate for this threshold behavior. And actually the nice thing about that, it is differentiable in all of the points, but in here we have discontinuity, which is actually not good, especially in backpropagation. And also we have zero gradients in here, which could interrupt the backpropagation algorithm. Okay, so now we want to talk about the sigmoid. The first problem of this activation function is that, as you could see, it saturates very quickly. In this, from this range to this range, we have some kind of nice activation function, or in here we have approximately a linear regime. After that, this activation function starts to saturating, and this is actually bad. Why? Because when we want to train the network, we use the backpropagation algorithm. And in backpropagation algorithm, if you remember that, in here we could see that when we have a sigmoid activation function, then we want to backpropagate the gradient. We should multiply. We should have a multiplication related to the derivative of the activation function. Okay, so because in here the derivative of the activation function is really low, because we have a really low slope in here, and so the derivative will be very small. So this will be very small, and so the training will be really slow, okay, because this term could be really small. Okay, so in other words, it is common to say that saturated neurons kill the gradients. So it means that this derivative will be really small when you use sigmoid activation function, especially in deep neural networks, because when we have multiple layers, these terms multiply together at the end, and it makes the situation worse. Okay, we will see that in vanishing gradients or exploding gradients. So the first problem of the sigmoid activation function is that it saturates really quick and so kill the gradients. And we could actually calculate the derivative of the sigmoid function really easily. And as you could see in here, you could write the derivative of the sigmoid activation function in terms of the function itself. So it is actually a really good thing about sigmoid, or we really like to have a simple derivative for the activation function. In this case, we have such kind of simple relation between the function and its derivative. In other words, if you calculate the sigmoid for an input, then you know its derivative, because you could calculate this easily. Okay. Okay. The second problem of the sigmoid is that the sigmoid outputs are not zero-centered, or in other words, as you could see, it does not have this shape around 0. We have 0 in here, and this could result in a problem that we will see. So in this case, if we have a positive input to the neuron and then apply the sigmoid activation function, and if you want to update the W, if you use the sigmoid activation function, then all of your gradients will be positive or negative to update. And in here you could see what's so bad about this. So if this is the optimal W direction that we want to update the weights along this direction, then because all of the inputs are positive or negative, all of the inputs are positive, then if we apply the sigmoid activation function, then we just have positive or negative gradient for all of the weights, which could create these pattern, right, as you could see in here. And this is zigzag problem, and this is one of the problem of sigmoid, and it is because it is not zero-centered activation function. Okay, so now we know about these two problems. The third problem of sigmoid activation function is that calculating exponent of x could be really a bit expensive computational wise for the device, GPU or CPU. Depends on what you use for training, but actually honestly I don't think it is a serious issue with the sigmoid, although it is an issue. But the most important issue personally I think is this one, because it saturates really fast and kills the gradients. The sigmoid is not actually a very good choice in deep neural networks. Okay. The second activation function is tangent hyperbolic. So when we use tangent hyperbolic, you could surprisingly you could write the tangent hyperbolic based on the sigmoid. So the tangent hyperbolic of x is, if you know about so if you remember from trigonometry, you could write the tangent hyperbolic as this, and also for sigmoid we have this. So you could actually write the tangent hyperbolic based on in terms of sigmoid, and we have this relation between these two activation functions. And if you plot the tangent hyperbolic, you could see something like this. It is between -1 and 1, so it is zero-centered now, which is nice about tangent hyperbolic activation function. So it does not have the zigzag problem, which is really good, but still it kills the gradient and saturates really fast. As you could see in here, we have saturation of the activation function, which kills the gradient and interrupt the backpropagation algorithm and slow training process. Okay. The next activation function, which is maybe one of the activation functions that is commonly used in deep learning, is Relu activation function, or rectified linear unit. It is actually a really simple activation function. It is maximum of 0 and x, which is simply x in here and 0 in negative regime. So now it does not saturate in this region, which is good. So we don't have vanishing gradient in here in this regime, and we could actually calculate it its output really fast, and so it is very computationally efficient. And also it showed that in practice neural networks with Relu activation function can converge faster, the reason is probably because it does not saturate. And just note that it is a nonlinear activation function. So your activation function should be nonlinear because we want to have the nonlinearity to able to build complex models. So we couldn't have something like this as the activation function. So actually we could have something like this, but it is not nonlinear activation function. And some researchers say that it is actually biologically also more plausible than sigmoid, and some neurons actually behaves like Relu activation function rather than sigmoid. So maybe that is not very important for us, okay? But let's discover more about this activation function. So if the activation function is Relu, then again we have this relation for the backpropagation. So let's say when we are in here or in positive regime, this is the derivative of activation function is 1, because for y is equal to x, the derivative is 1. Okay, so we have 1 in here, so we just have this term, so which is this one, or in other words, the gradient from the next layer goes through here without any change. Okay, but then we have in here the derivative is 0. Okay, so this is 0, and so this will be 0, and that is really bad. In other words, we don't have any gradient in here, and so the activation function Relu could kill the gradients in the negative regime, and we don't have any update in that iteration for the weights. Okay. And also, it is not zero-centered. As you could see here, we have 0 in here. So it is not zero-centered activation function, so we could have the zigzag problem again with Relu. Just note that still the Relu is more and far better than sigmoid and tangent hyperbolic, but it still has some problem. Okay, and the bad thing about this is that when we have a negative gradient, or let's say we are in here, because the gradient also is 0, we will stuck in here forever for that neuron, and we say that in this case we say that neuron is dead because it could never get rid of this point. Okay, because the gradient is 0, and so we couldn't update the weights in that case. Okay. To solve this problem, we have another activation function. It's called Leaky Relu. So in the positive regime, we have this y equal to x, so it is like Relu in positive regime. But in contrast to Relu in negative regime, we don't have 0 as the activation function. We have a low slope or small slope linear equation in here. So it could be 0.01 or a really small number in comparison with 1x, which is in here. So actually it is a hyperparameter that you could change, and you could actually adjust, and also maybe with cross-validation you want to optimize this alpha. So in parametric form we call it P-Relu, but so they are technically the same thing, but just this is a parameter for the activation function. Okay, and the good thing about this, it will not die when we have negative input. Okay. Another method to solve the problem of Relu is the Relu, or exponential linear unit. In this case, again, we have a Relu-like activation function in positive regime, but in the negative regime, we have an exponentially form of activation function in here. The good thing about this is that, again, we have a small slope in here, so it could help us to a neuron will not die during the training, and also it is a little more robust against noise in negative regime. So when we have a Leaky Relu or P-Relu, then when we have a really negative number, then this will be a large negative number. So if we have a noise in here, then the network will affected by this noise. But this is a more robust thing to noise technically, and so that is good actually. But because of exponential that we should calculate for x, it may be a little computational expensive for deep networks. And at last but not least, we have Maxout Neuron, or Maxout activation function, which is a generalization of Relu activation function, or parametric Relu, okay, that we have seen. In fact, if we put the W1 and B1 0, then it is like Relu. Okay, and with actually adjusting W1 and B1, you could get different like of activation function, and so it does not die in the based on W1 and B1, it does not die, but the number of parameters will be double, because you have W1 and B1 in here. So, and W1, the dimension of W1 depends on the dimension of X, so you are doubling your parameters. Okay, so to sum that up, you could use actually Relu for the first choice, and in that case you should be a little careful with your learning rate, because you should avoid to get in the negative regime, and if you have large learning rate, maybe you go to negative regime very quickly, or something like this happens. So you should be a little careful with your learning rate. And also you could use Leaky Relu or Maxout or Relu, but again, in my experience, practically maybe Relu and Leaky Relu is the most common activation functions that are currently used. You could use tangent hyperbolic, but don't expect too much as I write it here. Actually, I don't use tangent hyperbolic myself. Maybe for the output unit, if you want to have a range in -1 to 1, using tangent hyperbolic is a good idea. But for intermediate layer, I suggest that don't use tangent hyperbolic. And also for sigmoid function, don't use that because it kills the gradients in deep neural networks, and it is not really good. Okay, so this is about activation functions. Now we want to talk a little about data preprocessing, which is commonly used in deep neural network before you pass your data to the neural network. Okay, so let's say you have this kind of data. If you plot those data, you could think that you have an elliptical shape of data. So with zero centering the data, or in other words, by subtracting the mean from your data, you will have a zero center data, which is good. We will see that in the next slide, why this kind of transformation is good. And by dividing the data by standard deviation, you could have the same variance in each direction, which is also good. Okay, so to normalize the data, maybe this is the most common transformation. To calculate the mean of your data and the variance of your data, then remove the mean from your data and normalize the variance. Okay, and also just note that when you have the test data, you should use the mean and the variance of your training data to normalize your test data. Okay. Okay, so why we want to normalize the inputs? The answer is that, let's say we have something like this. When we have inputs with different ranges, so let's say you measure some data, and maybe your first feature is in the range of centimeter, the second dimension of your feature is measured in kilometer. Okay, then if you plot your data and plot the output, you will have something like this in the space as a contour of your activation of the contours of your cost function, which is really bad for the optimization. We saw that when you use gradient descent, you could have a zigzag problem for poor conditioning problem. But if you normalize your data, you could have a really nice looking contour in comparison with this case. So the optimization process will speed up. Okay, and you have an improvement in performance probably. So maybe you need to consider the normalization for your data. Okay, but in practice, actually, we just, especially in image, the CFAR or Cipher 10 is a data set for image recognition. In and object recognition. So for normalizing this kind of data sets, we actually don't divide the data by the variance or by the standard deviation. We just remove the mean. Okay, so we just do this transformation. Okay. Okay. And that's all about data preprocessing. Although we have learned other stuff for data normalization and data preprocessing in previous sessions, in deep learning, I think the most common thing is actually the mean removal, except that maybe you're having a very special kind of recognition or detection that for example, some kind of data preprocessing or certain preprocessing are more fit for your training. But otherwise, this is the most common data preprocessing and the most practical and easy one. Okay, so now we want to talk about weight initialization. So when you want to use the backpropagation and gradient descent to update your weights, you should choose an initial weight for your weights, okay, or a starting point. The question is how to initialize the weights of a neural network. One way is to actually weighted them equally and initialize all of them to 0. We will see that it is not a good idea to do that, and it could slow down the process of training really much, and so hopefully you will not do that. The first idea is using small random numbers. For example, you could use the Gaussian with 0 mean and a small standard deviation to initialize your weights. Okay, so this kind of initialization could work in the small networks, but for deeper networks it could cause a problem. Why? To get why, first we should see the relation in a multi-layer network. So we know that when when we want to calculate the output in a multi-layer neural network, we have this composition of activation functions, right? So first we have the activation functions on ZL. If we replace ZL with based on previous layer weights and the inputs, we could write ZL based on those, and then again write those based on the previous activation function, and so on. So you have a large composition of activation functions. Okay, so when you want to apply backpropagation algorithm to calculate the derivative with respect to one weight, then you will see that if you just write and plug those mathematical expression, you could see that you have the multiplication of the weights to derive the derivative, and so it could cause vanishing or exploding gradients. In other words, if you use large weights for your network initialization, then the multiplication of those will be really large. Okay, let's say all of them are 10 and you have, for example, 10 million of these parameters, then the multiplication of these numbers are huge. So the derivative will be huge, and in fact you have exploding gradient. Okay, so it is not a good idea. In contrast, also if you use small weights, you have vanishing gradients. Let's say you choose 0.5, 0.5, and you have again 1 million of these, then the multiplication of those will be 0.5 to the power of 1 million, which is approximately 0. So in this case, you have vanishing gradients, and you cannot update your and train your network. Okay. So let's see what happens in the histogram of the neurons when we initialize the network with, let's say, with 0 mean and with a Gaussian with 0 mean and 0.01 standard deviation, a 10-layer neural network with 500 neurons per layer. So in this case, if we use the tangent hyperbolic activation function, then you could see that in the input layer, you have approximately a 0 mean with 1 standard deviation, and because your weights are initialized with 0 mean and 0.01 standard deviation, this standard deviation will decrease really quickly. Okay, so when you plot the output of the layers, in here you have input layer, which is the distribution of your input, which has 0 mean and unit variance, because you probably normalize your data. But because your weights have 0 mean and 0.01 standard deviation or small standard deviation, then you are doing actually shrinking your distribution in here, and in the last layer you actually have 0 standard deviation with 0 mean output, which is really bad. And so probably the backpropagation algorithm will not work for this network. Also, if let's say we use a large standard deviation with 0 mean Gaussian initialization, in this case we could see that we have 0 and 1, because we use tangent hyperbolic, we have just -1 and 1 at the end for the output of layer, which is not really good. In other words, it means that your activation function is saturated. So we are in saturated regime, and so the backpropagation algorithm does not work properly. To initialize the weights, we have actually different algorithms. Maybe it is kind of a research topic, and lots of people work in this area. But one of the best way to initialize the weights is Xavier initialization. So the intuition about that is that when you want to write the output of a neuron, you calculate the linear combination of the previous inputs times the weights to have a good output distribution. We could adjust the output variance based on the number of inputs. Okay, so when we have larger number of inputs in here, we could scale down the variance to initialize the weights. Okay, so the initialization of Xavier is that we initialize the weights with 0 mean and 1 over the squared root of fan in, or number of, this is the number of neurons as the input of neuron. And this square root, the reason of that is that if you have AX, then your variance, if you have a random variable with Gaussian distribution, let's say it is mu and this variance, then for this random variable, which is AX, we have A2 sigma 2 as the new variance for this new random variable. Okay, so we have an root square in here, and when we in this case, if we draw the output distribution, now you could see that we have a nice distribution in each layer, or we are in this regime, which is really good and what we like to be in tangent hyperbolic. Okay. But when we use Relu, actually this nonlinearity or Relu nonlinearity, this could not be a good idea, because this region. So to solve this, it suggests that we use an extra factor of 2 to this formula to have this kind of distribution for the output layers. Okay, so as I mentioned, there are now lots of different kind of initialization for the neural network, and we learned about the Xavier, but there are also lots of other kind of initialization. I think, for example, the Keras by default use Glorot, although you could use other initialization for the weights of neural networks. We will see how to use them. So now you have the intuition about the weight initialization and how it could be important for your network. And yeah, that's it for this session. Now you know how the activation function affects your network and how to use the weight initialization for your network. Okay, hope to see you in the next session. Bye.